Anytime. There we go. All right. So let's talk about last week on Thursday. We had a quiz, right? So again, if you didn't finish the, if you weren't here for the quiz, stop by during my office hours. It is timed. So don't start it in Delta Math until you're ready to do it. And then I'll open up the Canvas page for you to submit your work, right? So for this quiz, I wanted work submitted so I can grade your work for partial credit. Second thing is our lecture that we did last time was on applications through modeling, which is basically word problems that have to deal with optimizing, right? That have to deal with optimizing. Optimization problems, trying to figure out what will give you the maximum area or the maximum volume, or what will use the minimum amount of area for the maximum volume. Those are all those applications through modeling, and they are important word problems. But as I was looking through the AP exam and topics that are going to be on there, word problems are going to be on there, but optimizing things are not really that big of a deal on the AP exam. It is something you do need to know, so I'm glad we went over it, but I don't think the problems I gave you were, the difficulty level for those problems that were on that homework were way more than what you need to worry about on the AP exam, right? The setup for those word problems, I feel like they were a little bit too much. So I'm taking that homework off. I put a line through it there. If you already started doing it, just submit what you've turned in already, and I'll still give you the credit for it. If you haven't started it, don't start it. It's not going to be crucial to your grades, so don't worry about that one. Just a heads up on that, right? So don't worry about the optimization word problems, but instead worry about today's word problems, which is what we're going to get into right now, the notes for today. So if you guys want to get ready, get set, here we go. Today's notes. They're word problems still, but these are related rates problems. Related rates are still word problems. It's just now they are relating, they're telling you the rate at which something is changing over time compared to something else changing over time. Okay, so in these particular cases, you have multiple variables. You don't have to worry about solving for just the height or just the radius or just the length or just the width, but you will be taking the derivative with respect to a dependent variable. I'm sorry, an independent variable, not a dependent variable. Independent variable. And usually the case is, since you're, if you guys are heard of rates before, like how fast something goes, right? Like miles per hour, or how fast you run is like meters per second or feet per second. It's always per unit of time, right? And that's what related rates problems are. It's just how a distance or measurement of something is changing with relation to time. Okay, and that's what we're going to be doing here. Okay, so I'm going to give you guys a chance here to write down these steps. These are usually the same steps for all of these related rate problems when you're dealing with them. Okay. Number one is, of course, always try to understand the problem. What's being asked from you? What is being there? What is being given to you, right? And usually when I do that, I combine that with step two, which is to try to find a mathematical model, meaning if you can get a drawing or a picture of it somehow, and then get an equation that relates all the objects that are there together, right? And then write an equation relating the variable whose rate of change you seek with the variables whose rate of change you know. This sounds more wordy than it needs to be. It's basically, once you have your equation, try to take the derivative of everything so that it has a equation that has it as related rates as opposed to just the equation that you were dealing with to start. So you'll see once we do a problem. You see once we do a problem. This one's a very fancy way of saying take the derivative. That's all it is, right? When you go from equation 2, once you get an equation written, step number 3 is to take the derivative of that said equation, but you're going to take the derivative with respect to time, so you end up with rates of change instead of just some random derivative that you're dealing with, right? Rates of change compared to time. Differentiate both sides of the equation implicitly with respect to time t. 5, substitute the values for any quantities that depend on time. And then number 6 is to interpret the solution, right? What does it mean? What do you have here? Is this thing traveling at a rate that's moving away from it, or is it getting closer? Is the distance between the two getting larger? Is the distance between the two getting smaller, right? It's usually the case. It's like, oh, is it getting bigger? Is it getting smaller? Is there more things filling in, or is there more things draining out? 2 years ago, when I first started teaching this, one free response question that was on the AP exam was for sure a related rates problem. And it had to deal with how fast sand was being washed up onto a beach and how fast sand was being washed off the beach. And it sounded weird, but it was a very, very simple related rates problem. Simple related rates problem. And it's always hard to talk about it afterwards. But anyways, let's go ahead and take a look at this problem right here. You guys are able to copy all this down? Is it okay if I move down? Let me know if you guys still need to copy it. I'm going to scroll down right now. If you still need some time, let me know. Not yet. All right. Give you a second to copy down those 5 steps. Okay? I'll give you a second there. And then Cheyenne joined a little bit late, but she participated on there. Let me get you that point, Cheyenne. Boom. Did you wake up sleepy this morning, guys? I woke up like super tired. I normally don't wake up sleepy. But today I did. All right. If you guys are, I don't know if you guys still know this or not. I keep bringing this up throughout the year, but just in case you don't know, right? If I ever move too fast and you're too shy to ask about it into the chat, which by the way, you should never feel too shy. I will gladly put this, the problem back on so you guys can copy it down. But if you are one of those people who are too shy to ask about this, because I'm about to move on right now, did you guys know that all of these notes are posted online for you? All of these notes are posted online, and they're live. They're live. So if you don't get it right now and you want it right this moment and I scrolled away and you're like, crud, I have to wait for them to post it. All these notes are posted live onto your Canvas page. If you go back over here to the home page on my Canvas page, it's right here under notes, period 3, notes right here. If you just click on period 3, it'll pop open OneNote onto a new tab for you. And the only thing is you have to make sure you're logged in with your CVU HSD account, which you probably are if you're in the Canvas page anyways, but just make sure you are on Google Chrome. Just makes it a lot easier. And once you click on that link, it will take you into OneNote, which is the app I'm using to write all this stuff down. And it defaults to the very first section that we had once this thing loads. Yeah, Sam, it is super slow and laggy. That's normal. That's normal. It's trying to load all the notes that we've had done so far, Sam. So you gotta like leave it and also don't have a bunch of other tabs open. So it's super laggy for me as well. So yeah, you give it like a good minute, and once it loads in there, click onto the unit that you want to go to, and then once you click on it, it'll take a while even for that. But most definitely though, once you have it open and you click on it and you load through it, you can see today is the new lesson right here, 4.5 related rates. And I'll go do something else, and then see here, bam, everything that we needed pops up right here. And you could just leave this open as well if you want. While I'm lecturing, you could open it beforehand. And if I draw something like here, normally if I do this, if my internet is fast enough, it'll pop open up onto there. Don't worry about it, Oscar. We're just doing our notes here, and you can, like I said, you can catch up on these steps that we have written out here. Just by looking at it online. Does it pop up over here? Oh, it's not popping up. What if I hit the refresh button? Oh, it's gonna take forever to load, isn't it? Well, while that's loading, I'm gonna come back over here to give everybody a chance to copy this down. Oscar, especially you, if you want to write down these steps or take a screenshot of it while it's posted on here, you can take a screenshot of it. I was trying to prove my point that you could always look up these old notes. All right. I'm going to go ahead and move on back over here. So we're going to be doing this example problem right here. a grass fire is burning in a shape of a circle. The radius of the fire is increasing at a rate of 6 feet per minute. How fast is the fire area? How fast is the fire area of the circle changing when the radius is 150? All right, I'm going to go back here and prove my point. Oh, God, it's taking forever. All right, we're just going to leave that alone. All right, so let's go ahead and take a look here. All right, for this problem. There's a lot going on there, but, you know, step one, try to understand what's going on here, right? We have a grass fire that's burning in a shape of a circle, right? So let's draw this circle for this fire right over here. Oh, yeah, you know what? I'm going to cheat. I have it right here. What if is it hold shift? Good enough, right? Good enough. There's my circle, right? With radius r. Does that look all right? That looks okay, right? So they give us a bunch of information there, right? They give us a bunch of information there. They tell us like the area of the circle. Well, they don't actually tell us that. They're just telling us that the fire is burning. That we can calculate the area of this fire, right? And let's see here. What else do they tell us here about this? They tell us that the rate at which the radius is changing, right, is 6 feet per second. Now, this is a difficult part right here. What would you say is that variable equal to? Normally, we would say just r is equal to something to say the radius is equal to something, right? But they're telling us that the radius of the fire is increasing at a rate of, so I wouldn't just use r here, right? I need to write r as a rate of change, right? So the change in radius compared to the change in time, right? That dr dt is the rate at which, so I'll write this right here, I'm gonna put this in my notes. Dr dt is the rate, right? The radius is changing over time. That's what that is. Now, Monica's getting a little bit ahead of me. 2 pi r is an equation that we are going to use. 2 pi r is an equation that we are going to use. And that's, give me 1 second before I write that one down here. I want to write down the rest of the information that's given to us. Actually, you know, I'll just write that down. Oh, you're right. 6 feet per second would be a really fast fire burn, right? 6 feet per minute makes more sense. But yeah, and then, yeah, good. Thanks, Brian. Thank you, David. Monica pointed out, well, what about this formula? 2 pi r. Wait, did you write 2 pi r? Oh, no, that's for the circumference. That's for the circumference, right? They're not asking about us to compare circumference. They're asking us to compare about area, right? Must have been a gender review. Wow, forgot that happened in the past year. But here, check this out. The area that we're looking at is going to be pi r squared. Pi r squared, not 2 pi r, right? Pi r squared. Now, how do I know that I'm dealing with area and not with the circumference, right? Well, that is a fair question, right? And the thing is, we just have to look at what we're comparing it to. We're comparing to the area of the fire. They're not comparing it to the ring or how large is the ring of the fire, right? They're just asking about the area of the fire. So we're going to be dealing with an area equation here. They also tell us that r is equal to 150 feet. Now, you got to fight this urge. This is a very strong urge that every student gets. You have this urge to, I don't know if you have it, but most of my students have this urge to plug in 150 straight into this equation to find out what the area is. Don't write this down. A lot of students get this urge. Don't do this. Don't do this. The question is not asking you how much grass has been burned. They're not asking you for the area of burned grass, right? If it was asking that, you go ahead and plug it in and you calculate the area of burned grass is equal to this right here. But they don't ask that. Can anybody tell me what is being asked here? What are they asking you to find in this problem? What are they asking you to find? What are they asking you to find? They're not asking you for the area of burned grass. They're not asking you for that. They're asking for the rate of change of what? They are asking you for the rate of change, but the rate of change of, now they give you the rate of change, the radius is changing, and Monica's pointing this out right now. They're asking you for the rate of change the area is, right? The rate of the fire area. That's right, Brian. You're looking for the rate of the fire area. So the thing is, it's supposed to be written like this, right? The rate of fire area, but that's just really annoying to write out. So normally when we write this out, it's the area changing with respect to time. So I'm going to write it like this. Instead of writing it as rate of fire area, right, over time, I'm going to write it out as dA dt, and that's what we're trying to find. We're trying to find the rate at which the area is changing with respect to time. Now, I want to go ahead and erase this right here. Right, we're not supposed to plug that in there, right? But we do have these pieces of information. We're told the rate at which the radius is changing. We're also told what the radius is at a specific time. Right? We're told what the radius is at a specific time. Now, I need to find out what dA dt is equal to. Well, here's the thing. I have an equation with the a there. You see that? There's my equation with the letter A, with the area right there. I can convert that area equation into an equation with what I'm looking for, the dA dt, right? Thanks to the calculus that we've learned here. And that's going to be this part right here. This is what I'm trying to make you guys see, right? This is the equation that relates the variables whose rate of change you seek with the variables whose rate of change you know. This is my equation right here, the area equation. It's relating the area to the radius. I need to find the rate of change of the area. I have the rate of change of the radius. So this is the main equation, right, of area equaling to pi r squared. But I need it as dr dt and dA dt. And in order for me to do that, I'm going to look at this equation and take the derivative of both sides with respect to time. Take the derivative of both sides with respect to time. And when I do this, please make sure, right? Please make sure to use the chain rule. When I'm gonna put it right here. Don't forget the chain rule. Don't forget the chain rule when you take the derivative of this thing. Because again, we're not taking it with respect to A, we're not taking it with respect to R, we're taking it with respect to T, right? So check this out. The derivative of A with respect to T is just going to be dA dt. That one's straightforward. Pi is a coefficient. I'm going to bring that along for the ride. And I'm going to take the derivative of r squared. You ready for this? The derivative of r squared is normally 2r, but the chain rule tells me to also multiply the derivative of r itself, and the derivative of r itself is dr dt. You guys okay with that? It goes back to a couple chapters ago when we learned about this, right? What we're taking the derivative with respect to gets affected, right? So you guys remember a couple of chapters ago when we did stuff like y was equal to x squared, right? Traditionally, we always took the derivative with respect to x, and we always ended up with, oh, that just comes out to be dy dx is equal to 2x, right? But if you took the derivative using the chain rule correctly, it's technically 2x dx dx, right? It's because the x inside is being taken the derivative with that x down there, and the dx dx just always cancel each other out, right? If we were to change this and we did it with respect to time instead, or t instead, or any other variable instead, this would be dy dt is equal to 2x, and then this would be dx dt. You guys see that? Dx dt. So you got to be careful with that, right? You got to be careful with that. So in this particular problem, when I took the derivative of r squared, it is 2r. That power rule still applies, but don't forget to take the derivative of the letter that the variable that you have with the respect of time and taken into account. Okay. All right. With that being said, if you guys look carefully now, doing this work gives us this new equation that has what we are trying to find, right? The dA dt. equal to some stuff that we can plug in. You ready for this? We already know some of these values. We know that r is equal to 150, and we know that dr dt is equal to 6 feet per minute. 6 feet per minute. So all we got to do is just plug in those values, right? Just plug in those values, and I'll figure out that, oh, dA dt is going to equal to pi times 2, or 2 times pi. And let's write it that way instead, Knockme. What are you doing as pi times 2? Right? I'm going to write this as 2 pi times r, and the radius at this particular time that we're focusing on, right? The rate of change at this particular time is 150 times the rate at which the radius is changing, which is 6 feet per minute. So plugging all that out, I'm going to get here dA dt is going to equal to, and I just plug this into a calculator, right? 2 times 150 is 300. 300 times 6 is going to give me 1800, and this is going to be 1800 pi. And then, of course, you need to put down the units for this, right? Put down the units for this. And how do you know what the units are? Well, there's a couple of ways to do this. If you understand what you're looking for, the units make a little bit more sense. For example, right, since I'm looking at the rate at which the area changes with respect to time, the area would be, in this case, since I'm dealing with feet, the area would be feet squared per how much is time changing by? Time is changing per minute. So the units for this one should be in feet per minute. If you have taken physics, or you are taking physics, you understand that you can use the units while you're doing the problem to calculate what your units should work out to be. So for example, right here, your r is supposed to be 150 feet. You see that? Your dr dt is supposed to be in feet per minute. If you multiply those units together, you end up with feet, right? Multiplying with feet per minute, and you end up in the top there with feet squared per minute, which is the units that you ended up with right here. Which, by the way, is the answer of that problem. That fire is growing at 6 feet per minute, at a rate of 6 feet per minute. That means the area of the circle is growing at 1800 pi feet squared per minute. That's how fast the area of fire is growing. So what I want you to take away from these problems is I'm not having you memorize, this problem in particular. I hope you guys understand that. What I'm hoping you guys are drawing from this is that these related rate problems are going to come in many ways, shapes, and forms, right? And you kind of have to figure out how can I connect what is given to me and how can I connect, what to find, okay? How can I connect what to find? And that's just going to take practice. Like every problem is going to be different, and I think that's the hardest part about this. You'll never get, you'll never get a problem that looks exactly like what we've practiced. And I'm telling you guys right now that on the AP exam 2 years ago, when they had the full AP exam, the free response question had a related rate problem on there, and it wasn't a hard one. They gave you functions, they gave you the equations. You didn't have to make them up, or you didn't have to know like equation of an area or volume. They just gave you the equation. But the problem was it was worded so difficult that most students didn't know what to do. And I want to get that. I want to make sure you guys get over that hump this time. So I don't know how to explain that. If you see something that talks about the rate is increasing as a function of time, you just kind of try to draw a connection between them. And then basically the steps are basically just list out what you know, and then list out what it is you're looking for, and see if you can make an equation that connects those two, right? That's usually the strategy I go with, because you'll never know what equations you have to deal with. That's hard to find out. But drawing a picture and getting all that down based off of that stuff, it's a little bit easier, right? All right, let's just do another problem. Let's just do another problem. Let me show you another problem. Let me show you another problem here. And I'll show you what I mean. So here we go. A hot air balloon rises straight up from the ground, from ground level, 500 feet from an observer, right? If the balloon is rising at 4 feet per second, how fast is the distance between the balloon and the observer changing 40 seconds after the balloon is released? 40 seconds after the balloon is released. I'm going to give you guys 2 minutes, not to solve this problem, but to list out, or actually, no, do me a favor. Let's go with 2 minutes just for this. Can you draw a picture and label the sides based off the information that's given here? Can you do that for me? Draw a picture of what this looks like. A hot air balloon rises straight off the ground. So if you guys don't know how to start this, could you at least just start off by drawing a hot air balloon rising off the ground, right? So here's the ground, right? I just drew a flat ground right here. And then a hot air balloon rising off it. Make your hot air balloon a little bit better. I'm gonna just erase that. We'll let you guys do it. I'll give you guys, let's go with 1:30 right now. Can you guys, on the Pear Deck, I'm gonna open up, let me open up a blank page. Give me a second there. And you guys, open up the Pear Deck. Draw a picture of this for me. Draw a picture of this for me. Draw a person standing there. Draw a hot air balloon rising from the ground. And just let me see, what shape do you have for me when you draw this out? Give it a shot. Give it a try. I'm not going to put anyone on blast. Don't worry if you get it right or wrong. Just try it out. Just draw this out. And if you don't have the link for the Pear Deck because you've closed it, let me put that link back in there. And I want to take a look at some of your examples. I'm going to give you guys some points just for trying to draw this out. Okay? Just some points just for trying to draw this out. Now your pictures are probably going to look different from mine, and don't stress about that. Just understand that it's not that big of a deal. It's just, everyone's picture will look a little bit different, but the math behind it will be the same. Okay? Let's take a second, draw those pictures out. Let me see it. All right. I'm going to give some people some points here based off of what I see you guys attempting. So it's okay if you're not done. It's okay if you're not done. I'm just going to give the points to the people who are attempting it. All right. We got David. We got Calvin. I got you. We got Shirley. I got you. We got Sam. Sam O. Where are you? Sam O. There you are. Brian V. All right. Grace. Got you. Monica. I got you. Kaylee. I got you. Jocelyn E. I got you. Joe. I got you. Boom. Max. Got you. Leslie R. Eric A. Aurelie M. There we go. Emily C. Ryan and Fatima. Yes, I got you guys. All right. I love your drawings, guys. I love your drawings. Let's take a look real quick here. Beautiful work. Beautiful work. I'm going to go ahead and share and show off what you guys have here. Let's take a look at some of your responses here. So here's a balloon. Very nice detail. And then you drew the observer directly underneath the balloon. Let's take a look over here. Same thing here. Balloon rising up. And they drew the observer directly underneath the balloon. That's interesting. This person didn't. This person drew the balloon over here and drew the observer 500 feet away. 500 feet away from the balloon. I like that. That's same thing here. The observer's off over here to the side. The balloon is rising over there, right? Another person who drew right here. I'm assuming they're going to put the observer down here, 500 feet below. 500 feet below. And we got to be careful with this. But yeah, oh, you guys even labeled the rate at which the balloon is rising. I like that. I like that. Ah, here we go. Here's an observer. I think you just wrote down the wrong number. They are 500 feet away from the base of the balloon that's rising at 4 feet per second. Good, 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 good. That's a beautiful stick man right there. Balloon right there, 500 feet away from where the balloon is rising, right? Same thing here. You got to be careful here. So this is a very common mistake, and you guys can actually see this, right? You guys can actually see this. A common mistake for this problem, right? And it has to do with the wording of it. I hate it when wording for problems are not as clear as they should be. A hot air balloon rises straight up from the ground level, 500 feet from an observer. So ground level is right here, right? And the hot air balloon is over here, right? And it's not 500 feet above the ground. It's just saying that it's rising straight up from ground level, right? Which is down here. And ground level is 500 feet away from this observer. Wow, that's a really big person if that's drawn to scale here. Let's just draw that like that. So there's that person, right? And they are technically 500 feet away from the ground where the balloon started rising. And that's what I hate about this particular problem. The wording for that is so sticky, right? It's just like, I thought they were saying that the person was 500 feet below the balloon, but they're not below the balloon. They're 500 feet from ground level where the balloon has taken off. So I'll say that again, right? A common mistake for this one is people will read this problem and they'll say that the observer is 500 feet below the balloon, but that's not the case. They're saying that the observer is 500 feet from ground level where the balloon is rising straight up, right? It's rising straight up. So it's not 500 feet underneath it. It's 500 feet from ground level where the balloon has taken off, like so. And Calvin, I agree with you. That is a lame thing, but it is something you got to be careful about. Okay? The wording for these things can be a little bit weird. How would it be worded if it were over the observer? It would I'd have to specify like that. It would just say like a balloon is rising above an observer. I would say above it or right over it. Usually it would be a little bit more direct. I know. I'm a little. Yeah, this one's a bad one. I don't think they're all like this. I think this one example right here, I think I should have found a way to reword that one to get that a little bit better. But yeah. So that's how I would draw this out. Okay. Now, if the balloon is rising at 4 feet per second, right? At 4 feet per second, how fast is the distance between the balloon and the observer changing 40 seconds after the balloon is released? So here's the thing. I'm not asking to see how fast is the distance changing from this way or this way. I'm asking how fast is the distance from the person or the observer is to the balloon. So I'm going to draw that line right now. I'm going to connect the person to the balloon like so. That's the distance that they're asking about. That's the distance that we're asking about. How fast is that changing? Right? And I'm going to call this distance right here, I'm going to call that C. The distance between the observer and the balloon, we'll call that C. Okay? Now, excuse me. This is going to be a little bit tricky. What would you guys label this right here? What do you guys want to call this right here? What do you guys want to call that right there? How high the balloon is. Oh, wait, I got a hand raised. Monica. H, B, whatever letter you want. Whatever letter you want. Z. Sorry, it was an accident. Don't worry about it, Monica. But I thought you were just raising your hand to answer the question. But either way, you can call it H because that's the height of the balloon. You could call it B because that's the height of the balloon. You could call it Z because it's the height of the balloon. That's all it is, right? I'm going to call it H. Let's call that H, the height of the balloon. And I have no idea what that height of that balloon is right now. I have no idea. None. None whatsoever. Actually, I do, but we'll talk about that in a little bit. What do we know from this problem, though, is that the rate at which the balloon is rising at is 4 feet per second. Is 4 feet per second. So I don't know what the height is, but I know at which the height is changing with respect to time, don't I? I know that the height, let's not write it like this. This is going to be, let's zoom out a little bit there, and let's make it down over here. The rate at which the height is changing with respect to time is 4 feet per second, right? The balloon is rising at 4 feet per second. So I know that right there. I know the rate at which the height is changing, right? They're asking me to find the rate at which this distance between the observer and the balloon is changing at. So I'm asked to find what is dc dt. What is that equal to? So that's the rate at which I know the height changing. The rate I need to find is the distance, the rate at which the distance is changing from the observer to the balloon. So I need some way, shape, or form to relate these two together. I need to relate c to h. I need to find a way to relate dc to dh. Do you guys see any type of equation I can write from this drawing that I have? What's something that I can look at? Area is an interesting one, but I'm not looking at the rate at which the area is changing, right? Which would just be 1/2 base times height, right? I'm not asking to find the area of that. It's not a bad try. It is a triangle, though. That is good. That is a triangle. Is there any other equations that you guys know about triangles that relate all of the sides to each other? You guys know any equations that relate the sides? Pythagorean Theorem. That's right. Brian, Areli, David, Grace. Very good. Very good. There's the Pythagorean Theorem. That relates all sides together, doesn't it? Right? Normally it would be a squared plus b squared equals c squared, but we're not using a and b in this case, are we? We're using h and whatnot. So I'm going to go ahead and use those guys right here. So when I do this problem out here, right? Instead of a squared, it's 500 squared, isn't it? Plus b squared, well that's just h squared in this case, is equal to c squared. It's equal to c squared. Now, we're not done, right? I need to relate the rate at which the distance between the observer and the balloon is changing and the distance the balloon from the ground is changing. So I need to, instead of have this as h and c, I need them to be dh and dc with respect to time. dh dt and dc dt. Can somebody help me out here? What should I do now that I have this equation to get it to be a related rate problem? I have this equation that relates the height of the balloon and the distance between the balloon and the person, right? What can I do to get this equation right here to be, instead of h and c, it'll be dh dt and dc dt? What could I do? What could I do, guys? What could I do? Follow the steps from before, right? Step 3, we wrote an equation that relates those variables. Step 4, do you guys see step 4? Differentiate both sides implicitly with respect to time. With respect to time. Don't solve it for h. Don't solve it for h, because we still don't know what still don't know what c is. So if we solve it for h, we don't have a c to plug in there, right? We don't have a c to plug in there. We were looking for just to find dc dt. That, remember, this is the ultimate goal. We're trying to find dc dt. Okay. So step 4. Take the derivative of both sides with respect to time. So we've drawn our picture. We've made a connection here. We've listed out what we know, right? And we're going to go ahead and take the derivative of both sides here. So we have here dt with respect to time. You'll notice that I'm not even going to bother finding out what 500 square is, because the derivative of that is still going to come out to 0. Taking the derivative of h squared is going to give me 2h. But again, don't forget the chain rule when you do this derivative. It's not just 2h, it's 2h dh dt, dh dt equals to 2c dc dt, dc dt. Remember, what are we trying to solve for? We're trying to solve for dc dt, right? So I'm going to go ahead and divide both sides by 2c. Divide this side by 2c, divide that side by 2c. The 2's are going to cancel out here. I'm going to end up with dc dt is equal to h over c times dh dt. You can write that as one big fraction, or you could write that off. You could write it like, you know what? Let's write it like this. So it looks dh dt all over c. Yeah, that's one way you could write it. We still have an issue here. I don't have what the h is, and I don't have what the c is, right? But I do have this thing solved for. dc dt is what we're trying to find. I have dh dt, don't I? I have dh dt. They tell us that dh dt was equal to 4 feet per second. So I have that piece of information. I need to find out what h is. I need to find out what c is. Well, let's go back and read the problem here. They don't tell us what the height is, by the way, do they? They just tell us that the balloon is rising at 4 feet per second. How fast is the distance between, so they start asking the question right there. How fast is the distance between the balloon and the observer? Ah, there's a piece of information here, isn't there? Changing 40 seconds after the balloon is released. So they do tell us something about time. They tell us time is equal to 40 seconds at this point. They tell us time is equal to 40 seconds. Is that enough information for us to solve this problem? They tell us that time is equal to 40, but I don't want time. I want the height at which that balloon has reached. And I also want the distance between the observer and the balloon at that specific time, t is equal to 40. Can anybody read this problem? Does anybody see where I can get the height knowing that the time is 40 seconds? Anyone got any clues, any ideas? The balloon is changing, remember, at a rate of 4 feet per second. And Brian is pointing out that if we multiply 4 by 40, what will that give us? Why? And also, why would you multiply 4 by 40, Brian? You are correct, by the way. You get the height. Think about this. dh dt is how fast the balloon is rising. So after 1 second, the balloon has risen 4 feet. After 2 seconds, the balloon has risen 8 feet. After 3 seconds, the balloon has rised? Those aren't the words I'm looking for. Has risen 12 feet, right? So at t equals 40, the height is going to equal to, you ready? The rate at which it's traveling, which is 4 feet per second, times the time that it's been traveling for, which is 40 seconds. Now, when you multiply this, the seconds will cancel out. You're left with h is equal to 160 feet. Knowing that the time was that, they tell us that the height of this balloon is going to be 160 feet at 40 seconds. Plug it into dh dt. Yeah, we are going to plug that into dh dt, but we need to also plug it. We also need to find out what h is, and this is a roundabout way of getting there. But you guys kind of see it, right? I meant the equation. Yeah. Be careful with that. Be careful with that. Yeah. All right. So we have h is equal to 160 feet. Boom. Now that I have that, I can plug that into here. We need to find one more thing, don't we? We need to find one more thing, and that's c. We need to find c. Oh, God, can someone help me here? Is there some equation that will help me find out what c is equal to if I know what h is equal to? And Brian's pointing it back right there. Let's go back to the Pythagorean theorem. Good old Pythagorean theorem, right? 500 squared plus h squared. But we know now h is equal to 160 squared is equal to c squared, right? Now I have that. Now I can plug that in and figure out what that is, right? So I'm going to go ahead and use my calculator for this because I don't know what well, I do know what 500 squared is. Isn't that like 250,000? I believe it's 250,000. And you know what? Let's just double check. Yeah, 250,000, right? Plus 160 squared. And that's going to be a total of that number right there. And I'm going to take the square root of that because I'm going to solve for c. So I'm going to go ahead and hit second, square root that said answer. And I get there 524.9. Let's see here. 524.9. How many decimal places I want to round this to? 976. 976. Students always ask me, how many decimal places should I round to? I always go to like 4 decimal places. If you want to be super accurate, just write down all the numbers. I know it's tedious because then you have a lot of numbers to write down. But honestly, no more than 4 is really necessary. But if you really want it to be super accurate, you could just let the calculator carry it through. So I found out what C is using the Pythagorean theorem. Now I have every piece of information, right? I have no missing things. I can plug it all into here, and I'll be able to find out what the rate of change, the distance between the balloon and the observer is with respect to time. All right, so I'm gonna go ahead and plug that in. By the way, this is in feet, right? So I'm gonna go ahead and plug this in. dc dt is equal to h, which is 160 feet, right? Times dh dt, which is 4. Wow, I was about to spell out 4. Knock me, what? 4 feet per second. And this is all being divided by 524.9761899 feet. Again, if you put the units in here, it's easier to see what your units are going to end up with. But again, it makes sense that if you're looking at the rate at which the distance is changing with respect to time, the units you should end up with is the whatever distance you're measuring with divided by whatever time you're measuring with. So these feet are going to cancel out, and you plug this into your calculator right here. I'll leave that decimal in there like that. So I have here 160 times 4 divided by that said answer, right? And that's going to give me 1.219 feet per second. 1.219 feet per second. Now, you still have to understand your answer. Just because we found the answer, right? You got to make sense of this. What does this mean? Is the balloon and the observer getting close to each other, or are they getting further apart from each other, right? Since my answer comes out as a positive 1.29 feet per second, that means at this particular moment in time, at 40 seconds, right, when the balloon has a height of 160 feet above the ground, the rate at which the distance between the observer and the balloon is getting larger, right? That positive number means that they are growing further apart from each other. The rate at which this is changing as 1.2 feet per second means that at this very second, the distance is changing 1.2 feet away from where he's standing. Now, is it going to be a consistent rate? No, it's not. It's not. And I wish we were in class to do this in person. It's actually a really interesting type of problem. If we were actually able to, you know what, I could find an example. It doesn't matter. But that's the idea here. Earlier, right, we found out that the area, dA dt was 1800 pi feet squared per minute. That means at this particular time when the radius was 150 feet wide, the radius was 150 feet wide. The rate at which the area was changing was 1800 pi feet squared per minute. That means that it was growing. And if this number was negative, then we would say that the area was shrinking, right? You can have that. You can have negative rates, right? Because the rate of change doesn't necessarily always have to be growing. It could also be shrinking. And that's what's going on over here. If this problem was a little bit different, right, and we said the balloon was going down, right, was decreasing at a rate of some number, then the distance between the balloon and the person would also be decreasing, and the rate at which the distance is changing from the observer to the balloon wouldn't have been positive. It would have been negative. So you got to understand, if your answer came out negative, you have to understand that for this particular problem, the distance between those two objects are getting closer, right? Whereas since it's positive, the distance between those two objects are getting further apart. And it's always going to change from problem to problem. Like, does that mean it's always going to be that it's a distance getting closer or getting closer or getting closer or getting further? Is it an area that's getting wider or smaller? And it all depends on the problem. I keep pointing it back to that one problem. That one problem from 2 years ago on the AP exam, it didn't talk about like distance getting bigger or smaller. The answer that they found was there sand being added to the beach, or was there sand being taken away from the beach, right? If they got something that was positive, they found out that the rate at which the sand was being washed up on the beach was more than the rate of sand being taken away from the beach. And that's what some of my students missed out on, was missing out on those points, understanding like it's not always about, you know, like, oh, they're going further or closer, or the area is getting bigger or smaller. Sometimes it could be things that's just quantities are increasing or decreasing. Another problem, and I thought this one was hilarious. I never actually saw this problem, but someone told me about it on an older AP exam. Their related rate problems had to deal with people getting on and getting off an escalator. And you're not going to write a Pythagorean theorem equation for people getting on and getting off an escalator. Instead, they just gave the students the function for the rate at which people were getting on an escalator and people were getting off an escalator. And you were supposed to figure out, like, you know, how many people are exiting this escalator and how many people are getting on this escalator at any particular time. Anyways, I'm getting sidetracked. I always get sidetracked, but hopefully you guys are looking at this problem. It's not too crazy of an idea, right? It's not too crazy of an idea. Let's try another one, and maybe this one you guys can give this one a shot. Okay, let's go ahead and go over here. Right here, let's go with this one. Let's make this wide like so. A 15-foot ladder is resting against the wall. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? So I'm going to let you guys draw this one out. I'm going to go ahead and clear out the screen again. Can you guys draw this one out? And let me see what you guys have for your drawing. I'm going to give you guys a minute here. So a 15-foot ladder is resting against the wall. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? 12 seconds after we start pushing. So I'll give you guys a second there to draw that out. The ladder is touching the ground, so yeah. Oh, beautiful. I'm going to go ahead and start giving you guys some points over here. And it's starting to look pretty good. Oh, man, you guys went above and beyond drawing your ladder. You know, I would have been happy if you just drew one of these and said that's the side of the ladder. Let's see here. We got some people here, and I'm going to go ahead and give you guys some points for attempting to draw it. We'll work on solving problems after we start working on setting up problems. Haley. IB. Belly. David C. Ryan M. Got you. Jeffrey. Beautifully drawn, Jeffrey. And Grace. Grace, are you drawing the ladder from a front point view? I mean, that's not wrong. It's just going to be a little bit more difficult. A little more difficult. All right, give these guys some points. Let's take a look real quick. Check this out. Let's see how people did. So, good. So here's the ladder. That person has really long arms. The ladder is 10 feet away from the wall. And the height of the ladder is we don't know yet. That's not bad. But don't forget to incorporate, right? Don't forget to incorporate. How long is the ladder? That also needs to be in there as well. Grace, yes. Okay, we're going to get to your drawing, Grace. We got to take a look at it. Good. Oh, not only does it label, you also show the rate at which the ladder is changing, right? As it gets towards and closer to it. It's 10 feet, beautifully labeled. The ladder itself is 15 feet, beautifully drawn, right? Beautifully drawn. Pushing towards the ladder, at 1/4 feet per second, it's 10 feet away. And putting in there that it is 15 feet for the length of the ladder. Beautifully done, beautifully done. Look at that notation right there. df dt. This person is going ahead and labeling this distance as f. I like it, I like it. Now, we're going to talk about that. That's a good label, though. That's a good label. But 1/4 feet per second is actually not the answer for the rate at which they have put there, that 1/4 feet per second. Although I said that incorrectly. It is correct. You can say it that way. You have the arrow drawn, so that's actually a good point. So yeah, I'm going to talk about that. Good drawn here. Good drawing here. So this person drew two drawings, and I like this one. It's 10 feet away to begin with the 15 feet of this ladder. The ladder is still 15 feet, by the way, but now the distance from the wall has changed, hasn't it? It's less than 10 feet because it's been pushed at a rate of 1/4 feet per second. So the height has also changed. Whoever did this, beautiful job, beautiful job. I appreciate that. That's awesome right there. 15 feet for the ladder, 10 feet away from the wall. Awesome drawing. Beautiful labels right here. Great use of your lines. Same thing right here. Beautiful. 15 feet for the length and 10 feet away from the wall. Awesome job. 15 and 10. Beautiful, beautiful. Drawing the ladder right now. Drawing your person. Don't forget to label it. 15 feet, 10 across. Awesome job. Wait, Grace, did you erase your drawing from front on? It was a pretty good drawing. I mean, I was impressed by it, but you did? Oh, I shouldn't have pointed. I shouldn't have said anything. It was a pretty good drawing from head on. If you're looking at the ladder it's just hard to do the math from that drawing. But anyways, so let's take a look at this problem here. We're probably not gonna be able to finish this in time because it is 10:31 here. But let's take a look here. All right. So this ladder is being pushed towards the wall, and that's right. Though there are two drawings for this one because at the beginning part of this drawing, right? At the beginning part of this drawing. The beginning part of this drawing, right? This ladder is like right here. It is about 15 feet, right, for that ladder, and is 10 feet away, right? And we don't know the height of this ladder at this point, do we? And we're asked to find out what the rate is as it goes up. So we're basically asking, what's the change in the height with respect to time? No, aren't we? Now, what do you guys want to call this base down here, right? So this thing changes, doesn't it? So after t is equal to 12 seconds, after 12 seconds, this thing is no longer 10 feet. It's been pushed closer. That's horrible, Naki. Did you not draw it so that there, right? This is still 15 feet, right? But this right here, I don't know what it is anymore, right? Neither is the height. This height has changed as well, right? I shouldn't call it h again, but I'm just going to call it h again. This height is no longer the same height as it was earlier either, right? This is height part 2. It's changed. What do you guys want to call this base? We know that base initially was 10 feet. What do you guys want to call the variable for the base over here where we don't know what the base is? What letter do you guys want to use? Monica's going with B. All right, we'll go with B. I like using X because X and Y direction, but B is perfectly fine. We're going to go with B then. Okay, we're going to go with B. So we're told that dB dt is equal to 1/4 feet per second. And this is where I'm going to let you guys know. Yeah, or X, Monica, thanks. This is what I'm going to let you guys know right now. Without any arrows or anything, this is going to be wrong. dB dt is not 1/4 feet per second. It's actually going to be negative 1/4 feet per second. And I'm going to pause there for a second and ask you guys, do you guys understand why dB dt is negative 1/4 feet per second and not just 1/4 feet per second by itself? Why is it negative in this case? Anyone have any ideas? It's decreasing. That's right. B is the distance from which the base of the ladder is from the wall. Since we're pushing the ladder closer to the wall, the distance between the two is getting smaller. So the rate at which it's changing is a negative rate. The distance is getting closer to each other, right? So it's not 1/4 feet per second. It's negative 1/4 feet per second. And that's all negative. If you think about it, negative and positive is really just a form of direction, right? It's just a form of direction. So if I knew that the ladder was going away from the wall, or like it was sliding away, then I would say that dB dt would be a positive 1/4 feet per second because it's increasing its distance. But in this case, it's decreasing its distance. Therefore, the rate at which the base is changing is going to be negative, right? So I have dB dt. I have dB dt. I'm trying to find dH dt. I'm trying to find dH dt. In order for us to do that, then we need to find a relationship between these sides here for this ladder. Anyone have an equation that relates all these three sides together? Anyone have an equation that relates all these three sides together? I have a base, I have a height, and then I have the 15 feet. Anyone have an equation that relates all these three sides together based off of what I have drawn here? Might help if I drew a little thing like that. Maybe that will help you guys. What's an equation that we can do? A squared plus B squared equals C squared. Pythagorean theorem again, right? Pythagorean typo or purpose. Pythagorean theorem, right? That's it. The two sides squared added together needs to equal to the third side squared because this house is this wall forms. Well, we're assuming that this wall forms a 90-degree angle, right? So b squared plus h squared is going to equal to 15 squared. What the heck knocked me? And I'm going to leave it there for now. We're going to continue this next time. Okay, I'm going to put this on pause because it is 10:36. If you guys want to, you guys can try to figure this one out. Just understand that b is not going to equal to 10 in this case. B is actually going to be equal to a smaller number, and I'm going to ask you guys to see if you guys can try to find that out. I'll be checking this pair deck just to see if you guys want to try it. If not, it's okay. Don't worry. We'll go over it next time. And yeah, that's going to be it for me today. I'll see you guys on Thursday. Remember, the homework for the optimization problems is no longer there. The homework for these related rate problems will be on Delta Math. If you guys want to check them out, I've already posted them on there if you guys want to check it out today. And just check out the videos that they have there and see if you can attempt them on your own. Okay, if not, we'll go over it on Thursday. And then that's it for chapter 4, guys. We're going to get ready for a test soon. So other than that, guys, have a good rest of your day. I'll see you guys on Thursday, all right? So long, guys. Have a good rest of your day. Bye-bye. Farewell. Sayonara. See you guys. Bye.